So the question here is, the molecular weight of a protein as determined by native phase is 400 kilodalton. This protein, when run on a non-reducing STS phase, here non-reducing STS phase means it does not contain beta-mercaptophenol, and gave a band of 200 kilodalton. And on a reducing STS phase, which means it will contain beta-mercaptophenol, which breaks the disulfide bond, gave a band of 100 kilodalton. The protein has, below are the given options. So let us solve this. So given native protein weight is your 400 kilodalton. Non-reducing STS phase gives your 200 kilodalton band, and reducing STS phase gives you 100 kilodalton. So since the native protein weight is 400 kilodalton and non-reducing STS phase gives 200 kilodalton, means it has two bands of 200 kilodalton each. 200 kilodalton, 200 kilodalton. So here no disulfide bond has been broken, so it gives two subunits of 200 kilodalton each. While when we add reducing agent like beta-mercaptophenol, the STS phase gives 100 kilodalton, means this 200 kilodalton has been again divided into 100 kilodalton each. 100, and this one too, 100 kilodalton, 100 kilodalton. So here we know there are 4 subunits, 1 2 3 4, and so here this one and this one are linked with disulfide bond. This one and this one are linked with disulfide bond. So this bond also breaks during reducing STS phase. And this are linked with non-covalent bond. So here I have tried to make 100 with disulfide bond, and this one with non-covalent bond. So let us look at the option. So in option D, it has been given that 2 subunits. In option C also 2 subunits has been given. So these 2 options cannot be true. And in option B, it has been said that they are linked with 4 disulfide bridges. But we saw that they have been linked by only 2 disulfide bridges. So option 1 says 4 subunits here, and of which 2 sets are linked by disulfide bridges. Yes, this option is right. As we have seen, these 2 sets, this one set and this is another set, these 2 sets are linked with disulfide bridges. So only 2 sets of disulfide bonds are there, and total 4 subunits are there. So 1 2 3 and 4. So your option A is your right answer. So let us move to the next question. It says a mixture of cytochrome C with molecular weight 11.7 kilodalton and myoglobin molecular weight 17.2 kb are to be separated by polyacrylamide gel electrophoresis. Their isoelectric pH PI values are 9.6 and 7.2 respectively. In which direction will each protein migrate at pH 8.5? To solve this, we know that the molecule whose pH is higher than the PI value, it will get the negative charge. So when pH is greater than its PI value, it will be having negative charge, and when PI value is greater than pH value, its overall value will be the molecule will be a positive one. So here cytochrome C has PI of 9.6 and they are migrating at pH 8.5. So in this case 9.6, that is PI is greater than pH 8.5. So PI is greater than pH 8.5, therefore the cytochrome C becomes positive. So since cytochrome C is a positive means it's a cation. Yeah, cation. So it's a positive, so it will move towards a negative. Cytochrome C will move towards negative, that is cathode. So cytochrome C will migrate towards cathode. So option A seems to be right. Let us check the myoglobin also. The PI of myoglobin is 7.2 and pH is the protein at which pH, the pH at which protein is migrating is 8.5, which is greater than 7.2. So we know that when pH is greater than PI, the charge of the molecule becomes negative. So this myoglobin becomes negative, so it will move towards anode. anode is the positive one. So option A, myoglobin will migrate toward anode and cytochrome C will migrate towards cathode. Option 1 is your right answer. So given pH is 8.5, pi of cytochrome. Cytochrome C is 9.6, cytochrome C is 9.6, and myoglobin is 7.2. So 8.5, 8.5, it is greater, and it is here pH is greater. So this becomes negative, this becomes positive. So it will move towards negative or cathode, and this will move towards anode or positive. So let us move to the another question. Here it says, from the data given below, identify the protein pair that would A. give the least mobility band on a sodium dodecyl sulfate polyacrylamide gel electrophoresis HSPACE experiment, and B. elute last on an anion exchange, that is example DEAE column respectively. So here basically what they have asked is, they have given us the molecular weight of the protein, and they have given us the pi of the protein. With the same concept of pi and pH, like in the previous question, we can solve this one also. And we have to find like which protein will have the least mobility, and also which will be eluted at the last in an anion exchange column. So to find the least mobility, we generally see the subunit molecular weight. We don't look at the native molecular weight, but we see at the look at the subunit molecular weight. So here, higher the molecular weight, mobility will be less. Higher the molecular weight, mobility will be less. So the highest molecular weight is here. Protein B is showing the highest molecular weight, that is 35,000. So it will have the least mobility. So least mobility was for A. So in A, our answer should be protein B. So A, protein C, this option is gone. This option is also gone. So these two options can be the answer. These two options can be the answer. Protein B, protein B. So we have to now find which will protein will be eluted at the last in an anion exchange column with the protein E or A. So when we look at this, the protein E is having its pi 3, while protein A is having pi 9. So obviously the pi here is less. Pi of E is lesser than that of A. So this E will be your negative, since pi is less than pi of E is less than that of A. So this E will be negative. So it will be eluted at the last. Since we know that anion is the negative one, so here most negative protein is your protein E. So protein E will be eluted at the last. So here our option 3 will be your correct answer.